At exactly 04:32 a.m. on November 23, 2025, radio silence was broken once again, but this time it wasn't just a signal, it was physics. 3I-ATLAS, already known for ignoring the sun's gravitational influence, resisting solar plasma storms and producing chemistry that mimics life, has now exposed something deeper, something mathematical, structural, engineered. Because when scientists began mapping its acceleration profile, its rotation dynamics, and the way it interacts with solar radiation, the numbers stopped making sense. No ordinary comet behaves like this, and as of this morning, there are now 5 separate physical principles being quietly re-examined because of what this one object is doing. This is not speculation, it's measured behaviour, and the deeper we look, the more it appears intentional. You're watching 3I-ATLAS, the only interstellar object that might not be a comet at all. Before we begin, drop a comment telling me what time it is where you're watching from, and which country or city you're in. This global network of quiet observers is helping track the greatest anomaly of our era. Now take a deep breath, and let's begin with what physics is trying to tell us. It began as a data point, a faint smear of light drifting against the stars, first detected by the ATLAS Survey Telescope network in Chile during the early hours of July 1, 2025. To most observatories, it looked like just another minor comet, dim, slow-moving and forgettable. But within 48 hours, that assumption collapsed. The early orbital data didn't match any known pattern. There was no looping arc, no elliptical return path, no signature of gravitational capture. Instead, every simulation pointed to a single conclusion. This object was inbound on a pure hyperbolic trajectory. And that made it something else entirely. In orbital mechanics, eccentricity is the measure that tells us what kind of path an object follows through a gravitational field. An eccentricity of 0 means a perfect circle. Anything between 0 and 1 means an ellipse, an orbit that repeats. Exactly 1 represents a parabolic escape curve, the edge case of gravitational influence. But anything above 1 indicates a hyperbola, an object not just visiting, but passing through, permanently. 3I-ATLAS had an eccentricity of 6.1. That number was beyond extreme. A value that high meant the object wasn't just wandering, it was slicing through the solar system at escape velocity, with no intent of turning back. Based on its trajectory and velocity, scientists quickly realised it was the third confirmed interstellar object ever recorded, after 1I Oumuamua in 2017 and 2I Borisov in 2019. But this one was different. The first surprise wasn't its speed, it was its precision. Most natural interstellar bodies, when influenced by the sun's gravity or solar wind, exhibit subtle deviations, tiny accelerations, tail asymmetries, outgassing jets that create rotational torque. But 3I-ATLAS didn't drift. Its motion, frame by frame, remained eerily stable. From its initial detection in July through its close approach to Mars in October, every updated ephemeris, the predictive model of its position, remained spot on. No corrections, no perturbations. It moved like a machine under control, not a natural object tumbling through gravitational currents. As more data arrived from optical and radio observatories, the precision became clearer. It wasn't just travelling on a hyperbolic path, it was travelling on a perfect hyperbola, with a velocity of roughly 60 kilometers per second in the sun's rest frame. That's fast enough to leave the solar system forever, and fast enough to ignore most gravitational influence along the way. For comparison, Voyager 1, the farthest human-made object, is moving at a fraction of that speed, and it took decades of gravity assist to reach escape velocity. 3I-ATLAS achieved it naturally, or perhaps artificially, depending on who you ask. But speed wasn't the only anomaly. Its angle of entry was nearly aligned with the ecliptic plane, the flat disk along which most planets orbit the Sun. That's statistically rare. Most interstellar visitors are expected to arrive from random galactic latitudes, not from within the plane of our own planetary system. This suggested one of two possibilities. Either it was an unlikely coincidence, something drawn from a cosmic probability well, or 3I-ATLAS originated from a system whose orbital geometry is strikingly similar to ours. Some theorists quietly proposed a third explanation: intentional targeting. It's a controversial idea, but the numbers continue to lean toward discomfort. The more precisely this object was tracked, the more it resisted any classification as a traditional comet. It was too fast, too smooth, too perfectly aligned. And in the back rooms of observatories and deep space tracking stations, a question began to take shape. Not out of hysteria, but out of necessity. What kind of object behaves with this level of orbital perfection, unless it was designed to? That question remained unspoken in most public briefings. But on the morning of November 23rd, it began to surface in the data, because from that moment forward, every physical assumption about 3I-ATLAS would begin to unravel. The event began in silence, on the far side of the Sun, where no Earth-based telescope could see. On October 25th, 2025, at precisely 0416 UTC, the first coronal mass ejection erupted from a region of intense solar activity just beyond Earth's line of sight. This wasn't a solar flare, it was something far more massive. A CME, a billion-ton wave of magnetized plasma, shot into space, carrying the energy of a planetary detonation. Then, just hours later, it happened again, and then again. 3 solar eruptions, one after another, each more concentrated than the last, and all of them, somehow, aimed in the same direction. That direction. The exact path of 3I-ATLAS. At first, solar physicists assumed it was a coincidence. CMEs can happen in bursts. Active regions on the Sun often produce chain reactions. But when satellites from Stereo A and the GOES-19 coronagraph network processed the data, something became clear. All 3 ejections converged on a narrow corridor in space, and the calculated intersection point matched the ephemeris of 3I-ATLAS within half a degree. In space physics, that's not close, that's bullseye. The object, already classified as the 3rd confirmed interstellar visitor to our solar system, was now entering the most dangerous zone imaginable, directly into the line of fire of the Sun's largest outbursts. Each CME was moving at incredible speed, the first at 800 kilometers per second, the second at nearly 1,000, and the third, most dense and narrow, at over 1,300 kilometers per second. At those velocities, the plasma would reach the object's position within 2 days, delivering not just radiation, but real mechanical force. For any normal comet, this kind of solar storm would be devastating. 1 billion tons of plasma slamming into an icy, porous object travelling at 60 kilometers per second. The result should have been instability, coma compression, tail disruption, or, if the object was fragile enough, fragmentation. But what happened next defied the laws of physics. By October 27th, as the storm fronts passed through the region, observatories began recalculating the trajectory of 3I-ATLAS, and every data point told the same story. No change, no wobble, no deflection, no acceleration. The object's velocity vector remained precisely the same, down to the arcsecond, when measured against its predicted path. It moved as if the CMEs had never happened. This wasn't just unusual, it was impossible. Every known object in the solar system, from comets to satellites to dust particles, is affected by CMEs. The plasma carries momentum. It couples with charged particles, compresses comas, disturbs magnetospheres. But 3I-ATLAS somehow remained untouched. Not even a delay, no deviation. 3 separate high-mass ejections from our Sun, each capable of altering orbits, failed to move a 3-kilometre wide body. At this point, scientists began to question everything. Was the object more massive than previously believed? That would explain inertia. But its brightness, coma, and density measurements didn't support that. Did the CMEs somehow miss? Coronagraph data said no. The alignment was too precise, too narrow, or was something more exotic at play? Some theorists began whispering about plasma deflection, the idea that 3I-ATLAS might be generating an electromagnetic field, repelling the solar plasma. That would make it not just reactive, but interactive, like a spacecraft with shielding. This wasn't just another comet anymore. The triple CME convergence of October 25th wasn't a solar event. It became a turning point, the moment this object stopped being an anomaly and started becoming something else, because the Sun had spoken, loudly, and 3I-ATLAS in perfect silence had answered. In physics, momentum is sacred. It cannot vanish. It cannot be ignored. When force is applied to mass, something must change. That is not just a guideline, it is one of the cornerstones of classical mechanics. But in the case of 3I-ATLAS, that principle broke. After enduring not one, but 3 high-velocity coronal mass ejections, the object's trajectory remained unchanged. No measurable drift, no slowdown, not even a detectable tilt. And that, for physicists, was worse than a mystery. It was a contradiction. Let's examine the numbers. Each of the CMEs observed on October 25, 2025, carried an estimated billion tons of plasma, magnetized, ionized material hurled through space at velocities exceeding 1,000 kilometers per second. The force involved isn't theoretical, it's been observed. CMEs distort planetary magnetospheres, they compress comas, they have thrown comets off course before. Even a small interaction, just a few % of the plasma mass striking a cometary nucleus, results in momentum transfer. It may not destroy the object, but it leaves a mark, a deviation in its arc, a change in its projected arrival time, or a tilt in its rotational frame. But with 3I-ATLAS, none of this happened. Within 48 hours of the last CME's expected impact window, multiple observatories recalculated the object's ephemeris, its precise path through space. Images from coronagraphs, infrared telescopes, and ground-based radar returned a unanimous result. It was still exactly where it was supposed to be. No delay, no offset. Frame by frame, its position matched the pre-CME forecast within observational error margins. The models did not need adjusting. There was no compensation for impact. The object behaved as if it had been untouched. And that's the problem. Basic orbital mechanics tells us this should not be possible. Even in the most conservative scenario, where only 1% of a CME's momentum couples into the comet, the expected result would be a velocity change of 1 to 2 meters per second. That might sound small, but in space, even a tiny delta V compounds over time. A shift of 2 results in a positional error of over 170 kilometers within 24 hours. After 3 days, over 500 kilometers, and yet 3I-ATLAS never deviated by more than a few hundred meters. Some suggested that the object was denser than expected, perhaps metallic, not icy, but its coma behavior, infrared signature, and outgassing rates contradicted that. Others proposed the CMEs missed, but again, trajectory overlays from Stereo A and GOES 19 show near direct alignment. If they missed, they did so by less than a fraction of a degree. So what's left? A theory now circulating quietly among plasma physicists and mission analysts proposes something more exotic. They call it momentum shielding. The hypothesis goes like this. The object is not resisting force through mass, but through field interaction. In other words, it may not be absorbing the momentum of solar plasma, it might be redirecting it. The coma itself, rich in ionized carbon dioxide and exhibiting structured outgassing, could be forming a temporary magnetic barrier, not unlike a magnetosphere. This field, if it exists, would act like a lens, dispersing or bending incoming plasma around the nucleus. That would explain the lack of tail compression, the zero deflection, and the perfect continuation of its outbound path. But there's a deeper implication. If the plasma didn't transfer momentum because of a field interaction, then 3I-ATLAS isn't just resisting solar interference, it's actively modifying it. This would not make it a comet. It would make it a system, a configuration of mass and field behaving intentionally or coherently. No known natural object behaves this way. And yet, it's happening. On paper, the laws of motion were not violated, but they were redirected, transformed, re-expressed in a form we've never seen from a body that does not belong here. Physics demanded a response. 3I-ATLAS gave us none. And that silence speaks volumes. When something doesn't move, physicists assume it's heavy. That's a fair starting point. An object with massive inertia requires more energy to accelerate or deflect. So when 3I-ATLAS passed through not 1 but 3 coronal mass ejections, without even a hint of momentum change, the first assumption was simple. Maybe it's just more massive than we thought. That would explain the silence. If 3I-ATLAS were 10 or 20 times heavier than estimated, the billion-ton solar plasma storms could pass through with minimal impact. Its motion would barely shift, no drama, no deviation. But then came the data. On July 21, 2025, the Hubble Space Telescope captured high-resolution images of 3I-ATLAS at roughly 2.5 astronomical units from the Sun. Using standard photometric modelling, based on brightness, reflectivity and coma intensity. Astronomers estimated the nucleus diameter to be about 2.8 kilometres. That's on the small end for a comet, but not unusual. The problem wasn't its size, it was its reflectivity. The object's albedo, its ability to reflect sunlight, was low, very low. The surface appeared dark, consistent with porous carbon-rich dust, the kind found on typical icy bodies. When combined with its estimated size and dust density, the total mass came out to roughly 5 trillion kilograms. That's large by terrestrial standards, but small enough that a single well-aimed CME should have knocked it off track, but it didn't. And that's when astronomers began asking a more uncomfortable question. What if we're not seeing the whole object? It's possible that 3I-ATLAS is shrouded in something darker than dust, a shell of material that absorbs more light than it reflects. If the outer layer were made of highly absorptive compounds, say exotic carbon chains or non-reflective mineral composites, it would appear smaller and dimmer than its true size. Another possibility, the object's shape could be highly elongated, like an interstellar cigar or monolith. A long, narrow body rotating along a central axis might confuse reflectivity models, leading to an underestimation of surface area and mass. A more massive object would resist deflection, but it would also require a structure we've never seen in natural comets. Still others turn to composition. If 3I-ATLAS were made of nickel-iron alloys, materials common in metallic asteroids and planetary cores, its density could be 8 to 10 times higher than ice. At those levels, the same 2.8 kilometre object would weigh over 70 trillion kilograms, enough to ignore even the strongest CME. But here's the contradiction. Active comas don't come from iron. For an object to be shedding gas and dust near the sun, it needs volatiles, substances like water ice, carbon monoxide or carbon dioxide that sublimate under solar heating. Metal doesn't sublimate, and yet 3I-ATLAS has an active coma, rich in carbon dioxide with tail jets and structured outgassing. That behaviour requires something soft, porous and volatile, not a dense metallic core. So which is it? Is it a lightweight ice ball shedding gas, or is it a heavy, darkened mass evading deflection? The reality might be something in between, or something entirely outside the bounds of known cometary physics. One theory proposes a layered core, a dense internal mass surrounded by a porous volatile shell. Think of a metallic seed wrapped in a dusty snowball. This would allow for both resistance to momentum transfer and gas production near the surface, but such structures are unprecedented in our solar system. Another, more radical theory suggests a hollow shell, a thin outer body stabilised and engineered for flight. That's not science fiction anymore, not after the way 3I-ATLAS shrugged off solar force like a drone cutting through wind. So, we return to the question, is it too dense, or is it something else? Because if the mass doesn't match the motion, and the surface doesn't match the chemistry, then the object may not match any category at all. And in science, when a thing can't be classified, it usually means we're looking at something new. At first, the absence of movement was explained away by mass. Then it was blamed on trajectory. But when the data ruled out both of those possibilities, when 3I-ATLAS stood still through 3 converging solar eruptions, something else had to be considered. Something that until now belonged only in theory, plasma redirection. To understand how bold that idea is, we need to look at how coronal mass ejections interact with matter in space. A CME is not just hot gas. It is a moving wall of charged particles, billions of tons of plasma threaded with magnetic fields. When this wave encounters a planet, it collides with the magnetosphere, bending and compressing it, sometimes tearing open cracks in the protective field. The result is auroras, radiation storms, and mechanical drag on satellites. But comets don't have magnetospheres. They're vulnerable. When a CME strikes a comet, it compresses the coma, distorts the tail, and, if the timing and angle are right, transfers momentum directly into the nucleus. This is not hypothetical. It's been recorded dozens of times across the past 2 decades. Comets have had their tails stripped, their trajectories altered, their structures fractured. 3I-ATLAS didn't just resist. It appeared to do something else. It redirected. Images from Stereo A and GOES 19 show more than just stability. They show something unexpected in the structure of the CME itself. The plasma fronts, normally wide and radial, appeared curved around the object's path. The wave fronts bent, Not sharply, not dramatically, but enough to suggest deflection. That's not what we expect from interaction with a small icy body. That's what we expect from an object generating a plasma sheath, an envelope of ionized gas interacting dynamically with incoming energy. This is where the idea of electromagnetic redirection enters. If the coma of 3I-ATLAS is more than just dust, if it contains a charged particle field shaped by internal currents or asymmetric gas jets, it could in theory function like a magnetic buffer, a field that absorbs incoming plasma, reionizes it, and disperses the momentum laterally rather than linearly. Think of it like an airfoil. The force doesn't hit head-on, it slides around. Some theorists point to a known but rare effect, induced magnetism in cometary atmospheres. As solar wind passes through ionized gas, it can generate brief, localized magnetic interactions. These aren't strong enough to block CMEs, but they can guide plasma under the right conditions. What makes 3I-ATLAS different is the scale. The coma's carbon dioxide emissions have been measured to be unusually structured, not radial but directional, jet-like. This could create asymmetric charge density, turning the coma into a soft field of polarized plasma. A plasma field with structure behaves differently from one without. It reflects, it refracts, and under extreme conditions it can repel. This would explain the undisturbed trajectory. The CME didn't miss, it hit the sheath and was diverted before it could reach the solid core. But there's a problem. Nothing in known natural comet physics supports this level of shielding. The field would have to be stable, coherent, and adaptive across a moving body in a rapidly changing electromagnetic environment. That would require feedback. It would require control. And that raises a possibility even more radical than mass discrepancy. That 3I-ATLAS may not just be an object with passive chemistry. It may be a system, engineered or evolved, to interact with solar plasma not by absorbing it, but by deflecting it. Not with armor, not with brute force, but with field physics we've only just begun to understand. Because if what we witnessed on October 25th was real, and the CMEs truly bent around the object, then this is no longer a comet resisting a solar storm. It is something else altogether, something that knew how to survive it. Every comet breathes. As it nears the sun, frozen volatiles in its surface begin to sublimate, transitioning directly from solid to gas. The result is a halo of vapor and dust called the coma, along with a tail that stretches away from the sun, pushed by solar radiation and wind. This process is chaotic by nature. Random fissures open, pockets of gas explode, jets erupt in all directions. That's what we see in every known comet, irregular outgassing driven by thermal gradients and surface inconsistencies. But 3I-ATLAS doesn't behave like that. Its outgassing is structured. From multiple observation platforms, including Hubble, JWST and ESA's ExoMars orbiter, data shows a remarkable consistency in the direction, frequency and stability of its jets. Instead of random eruptions, 3I-ATLAS displays what scientists are calling rotational phase-locked emissions. Here's what that means. The jets don't fire at random angles. They emerge from specific sectors of the nucleus, and they do so in predictable intervals. That implies that the object either isn't rotating, or that its rotation is being deliberately controlled. Let's consider the first scenario. If 3I-ATLAS is not rotating, or rotating so slowly that its orientation to the sun remains nearly constant, then localized heating could result in continuous outgassing from the same zones. That would be odd, but not impossible. However, analysis of Doppler shift data from the James Webb Space Telescope suggests small but measurable rotational dynamics, just not the kind we expect. The object isn't spinning freely. It appears to be maintaining orientation, as if it's locked in place relative to the sun's magnetic field. That's not normal for an icy rock. That's what attitude control systems do on spacecraft. Now consider the second scenario. If 3I-ATLAS is managing its own outgassing, directing it like miniature thrusters, that would explain both the structure and the trajectory stability. These jets would not just vent gas, they would steer. And if synchronized properly, they could create not only momentum compensation, but also plasma shaping in the coma. Which brings us back to what telescopes are seeing. The coma is not expanding symmetrically. Its density peaks along specific vectors, and it fluctuates in pulses, as if the jets are modulating output in response to solar input. In other words, It's breathing, but with rhythm. This structured behaviour has never been observed in natural objects of this class. The closest analogue is Comet 67P Churyumov-Gerasimenko, observed by ESA's Rosetta mission. That comet showed complex but still fundamentally random outbursts tied to shadowing and surface erosion. 3I-ATLAS is cleaner, more refined. It's not fragmenting, it's not flaring, it's not spinning wildly. Instead, it's responding, subtly, precisely, and repeatably. Some observers propose that internal layering within the object could explain this, a stratified structure, where only specific compounds near the surface are releasing gas. But that wouldn't account for the geometric consistency of the jets, nor would it explain the directional force balance. Even as gas escapes, the object does not tumble, it does not veer, it maintains course integrity, a feat nearly impossible without compensatory feedback. That feedback could be natural, but it feels controlled. And if it is, that reframes the entire narrative, because outgassing has always been treated as a byproduct of solar heating. But in this case, it may be a tool, a mechanism not for survival, but for navigation. In a solar system that batters comets into fragmentation, here is an interstellar object using its own chemistry to stabilize, to steer, to remain untouched. Structured outgassing isn't just a curiosity, it's a sign. And we're just beginning to understand what it might mean. Everything that drifts through space rotates. That's not philosophy, it's physics. From asteroids to moons, from artificial satellites to ancient comets, every known object exposed to solar torque, collisions, or internal asymmetry ends up spinning. Sometimes slowly, sometimes chaotically, but always rotating. Except 3I-ATLAS. Or rather, it's not clear that it rotates at all. When early light curve analysis was conducted on the object during July and August 2025, observers noticed something strange. There were no periodic dips or spikes in brightness. Normally, as a non-spherical body spins, its reflective cross-section changes. The sunlight hitting its surface bounces back differently as it tumbles, creating a predictable brightness wave. That wave is what astronomers use to determine rotational period. But with 3I-ATLAS, the light curve was flat. Not smooth, not slow, flat. This initially led some to assume that the nucleus was spherical, a rare shape for comets, but not unprecedented. Others proposed that its rotation axis was perfectly aligned with our line of sight. If that were true, we would see no change in brightness, because its shape wouldn't present a changing face. But neither theory holds up under scrutiny. High-resolution imaging from Hubble and spectral analysis from JWST suggest that the nucleus is not a perfect sphere, nor is its geometry simple. There are shadows, protrusions, brightness gradients across the coma. These wouldn't exist if the body were entirely symmetric or perfectly aligned. So if the object isn't spherical and isn't aligned, why isn't it spinning? Or, more unsettling, what if it is spinning, but in a way we can't detect? Further analysis of the coma and outgassing jets revealed another anomaly. The gas emissions were occurring from the same locations over multiple observation windows, days or even weeks apart. That suggests a stable orientation relative to the Sun, not just spin stability, but solar-locked orientation. This kind of behaviour is only seen in orbiting satellites with active stabilisation, devices that use gyroscopes, magnetic fields, or gas thrusters to maintain their alignment despite external forces. But 3I-ATLAS isn't in orbit. It's on a hyperbolic escape trajectory, moving at 60 km per second through the solar system with no return path. And yet, it holds its orientation. The implications are extraordinary, because orientation requires energy management. Outgassing alone can alter an object's spin. One-sided sublimation produces torque. If the jets aren't symmetrical, and in 3I-ATLAS they're not, then every burst of gas should be pushing it into a spin. This is how comets tumble. It's why we've observed rotational acceleration and chaos in hundreds of known objects. But again, 3I-ATLAS refuses. Its lack of spin evolution is more than strange. It's a violation of expected angular momentum dynamics. Something is maintaining its attitude, or something is absorbing the torque. Could internal mass redistribution explain it? Possibly, if the object had a liquid core or complex density layers, but thermal models suggest the object is frozen solid, with no interior mobility. so that explanation collapses. Could it be that we're only seeing the coma and the nucleus itself is rotating behind it? Unlikely. The jets emerge from fixed points. Their repeatability suggests surface-fixed emission zones, not a swirling mass. And radar imaging, though limited by conjunction, shows no smear or signal blur indicative of fast rotation, so we're left with one viable conclusion. 3I-ATLAS is either not rotating, or it is actively resisting rotation. And that distinction matters, because a natural object resists nothing. It yields, it spins, it evolves. But something with internal control systems, however primitive, can resist. It can stabilize. It can maintain direction, even under pressure. And that's what 3I-ATLAS appears to be doing. The rotation problem isn't just a data gap, it's a quiet refusal, a message written in motionlessness. And the more we observe it, the louder that message becomes. If an object is moving, it tells you, not in words, but in frequency. The Doppler effect, first described in 1842, is one of the most reliable tools in astrophysics. When an object moves toward you, the light it emits compresses. Its wavelengths shift toward the blue end of the spectrum. When it moves away, the light stretches, shifting red. This principle allows scientists to measure the motion of galaxies, exoplanets, and comets with astonishing precision. And when applied to 3I-ATLAS, it revealed something strange: early spectral analysis. From the James Webb Space Telescope, operating in the infrared band showed typical signs of motion. As expected, 3I-ATLAS was travelling on a hyperbolic path, approaching perihelion at roughly 60 kilometers per second. But when researchers began mapping the Doppler profiles of various emission lines in the object's coma, specifically those tied to carbon dioxide and hydroxyl radicals, something didn't fit. The curves were distorted. In a natural tumbling object with asymmetric outgassing, the spectral lines show slight broadening. This happens as different parts of the rotating surface eject gas at slightly different velocities, adding turbulence and thermal noise. It's expected, it's modelled, and it helps calculate spin, jet direction, and internal activity. But the emission lines from 3I-ATLAS were too clean. They were narrow, unnaturally narrow, and centred in a way that defied the rotational expectations. Instead of broad Doppler wings and chaotic shifts, the curves held stable central peaks, as if the emissions were coming from a single fixed velocity vector. That shouldn't be possible for a cometary body with complex jetting behaviour, unless the object is maintaining a fixed velocity orientation, not just in bulk motion, but in microscale gas output. The implications are deep. It suggests not only that 3I-ATLAS is refusing to tumble, but that its gas jets are compensating for velocity shears in real time. This implies feedback, and in natural systems that only arises in large planetary atmospheres, not icy kilometre-wide interstellar bodies. Researchers initially suspected instrumental error. Could Webb's spectrometer have miscalibrated the lines? Could thermal interference have blurred the readings? But cross-checks with Earth-based instruments, including ALMA in Chile and the IRAM 30-metre telescope in Spain, confirmed the same shape: stable, single-peak emission lines, locked to a consistent redshift. Even stranger was what happened as the object rounded the Sun. In most cometary passages, the Doppler curve shifts smoothly over time, reflecting the curve of the orbit and the increasing rotational chaos as surface erosion accelerates. But in 3I-ATLAS, the shift was linear and clean, like a spacecraft adjusting its velocity relative to an observer, not a tumbling comet, a guided object. Some astronomers proposed that the gas jets were emerging from a ring-like vent system, jets located symmetrically along the equator, evenly spaced, venting at equal pressures. That could theoretically mimic clean Doppler curves. But even if true, it raises a deeper question. What natural object has that level of symmetry? Nature isn't precise. It's messy, asymmetrical, worn by time. But 3I-ATLAS is quiet, balanced, structured. It is not broadcasting a signal, but its spectral lines might be something more subtle, a message in motion, a pattern that only reveals itself in physics, not language. To most observers, Doppler shifts are just numbers, velocities, math. But here, they may be something more, a signature, an imprint of control. Because if the jets of 3I-ATLAS are firing in ways that preserve not just orientation, but frequency stability, then something, or someone, wants it that way. Light reveals more than just shape, it reveals intention. When solar radiation strikes a physical object, it casts shadows, and from those shadows we can learn about dimensions, surfaces, even internal structure. It's one of the simplest techniques in astronomy, and one of the most powerful. But in the case of 3I-ATLAS, shadows introduced more questions than answers. On November 4th, the SOHO-LASCO C3 coronagraph captured a unique frame of the object as it passed near the Sun's outer halo. Coronagraphs work by blocking out the solar disk, allowing faint haloed objects, like comets, CMEs, and solar streamers, to be recorded in silhouette. When 3I-ATLAS entered the field, scientists expected a diffuse shape, a cometary blur, consistent with an icy nucleus surrounded by a bright coma. Instead, the shadow was clean. It wasn't an ellipse, it wasn't a smudge. It was an angular silhouette with flat edges, defined corners, and a geometry that no natural comet has ever displayed. The initial assumption was pixel error. Coronagraph data is noisy. Particles, cosmic rays, and compression artifacts can all cause false shapes. But adjacent frames showed no such anomalies, and as the object continued its path, the shadow persisted. Same size, same outline, same impossible geometry. Some described it as hexagonal, others as a flattened rhombus, possibly even a prismatic trapezoid. Whatever it was not spherical, and not the ragged, asymmetrical shape typical of comet nuclei. The object had flat surfaces. Even more telling, as it rotated, or rather as it appeared to maintain orientation, the shadow did not distort. That rules out tumbling. It suggests that the object was deliberately aligned in a way that kept one plane facing the Sun. And that alignment persisted across multiple instruments, including Stereo A's heliospheric imager. This is where it gets stranger. The geometry of the shadow did not match any previously recorded comet, asteroid, or trans-Neptunian object. Scientists attempted to model possible explanations. Was it a fractured nucleus with straight clefts? Could it be an overlapping frame of light and dark regions? No model fit the data. And then came the most controversial observation. In one sequence, during a brief coronal dimming event, a secondary shadow appeared beside the primary. Not behind, not trailing. Beside, as if another object was travelling in tandem. A twin or a reflection? Some researchers proposed that this could be an artifact of the coma, an asymmetrical gas cloud projecting a secondary silhouette. But coronagraphs don't record reflected light from gas. They capture opaque interference, and to create such a shadow, the material would need to be dense enough to block solar rays. That rules out typical gas. So the theory emerged. Perhaps 3I-ATLAS is not a single object, but a multifaceted system, made up of flat planes or interlocking segments, rotating or shifting just out of our resolution range. That would explain the repeating shadow, the persistent angles, and the suggestion of modularity. What kind of natural object casts straight-edge shadows in a curved universe? None that we know of. And while some physicists caution against overinterpreting grainy data, others see a pattern, an emerging consistency in how 3I-ATLAS defies geometry, gravity, and now light. The term shadow geometry isn't just poetic, it's a technical puzzle. Because if light cannot pass cleanly through the coma, and shadows persist under changing exposure angles, then the object must have surface properties, angles, textures, planes, that are interacting with solar energy in ways not consistent with known materials. In every frame, 3I-ATLAS seems to be showing us not just mass, but design. Not intention in a human sense, but structure, form, planning. The shadow shouldn't matter. But in space, when light outlines something that physics can't explain, it often means the truth isn't what we thought. Comets have tails because the Sun commands it. As an icy body approaches the inner solar system, solar radiation and solar wind begin to erode the outer layers, sublimating ice, lifting dust, and generating long glowing trails that stretch away from the Sun. The physics are clean, predictable, and visually dramatic. One tail, always pointing anti-solar, driven by pressure. But 3I-ATLAS introduced a problem, because its tail doesn't follow the rules. On October 26th, astronomers operating the Nordic Optical Telescope in the Canary Islands captured a series of long exposure images of 3I-ATLAS. At the time, the object was emerging from perihelion, when tail formation typically becomes most intense. But in the resulting composites, the tail appeared to be angled toward the Sun. This wasn't just misalignment, it was reversal. At first, observers assumed they were seeing a forward scattering effect, a trick of perspective caused by bright particles curving back into view. But as the object moved across the sky, the tail's orientation remained fixed, locked to a path that suggested solar alignment, not deflection. More concerning was what followed. Images from amateur astronomers in Chile, South Africa and New Zealand confirmed the anomaly. The tail wasn't swinging. It was anchored, bending in directions that should be impossible under standard solar radiation pressure models. That's when a second feature appeared, a secondary stream, directly opposite the first. This twin structure, commonly referred to as an anti-tail, is not unknown in cometary science. Anti-tails form when larger dust particles, released earlier in the comet's path, drift slower and remain closer to the orbital plane. Under certain viewing geometries, these particles appear to point toward the Sun, creating the illusion of a tail reversal. But in 3I-ATLAS, the anti-tail was sharper, longer, and more coherent than the primary, and worse, it led the object. Instead of trailing behind, it formed a structure ahead of the nucleus, stretching along the orbital path with unnatural rigidity. That doesn't happen with dust. Dust diffuses, it bends, it trails. But this stream was straight, stable, pulsing, even, according to time-lapse data from the Sloan Digital Sky Survey, which noted periodic brightness fluctuations at 8-minute intervals. This gave rise to the theory that the leading stream was not dust at all, but a form of ionized particulate or even low-frequency plasma beam. And here's the problem. No known natural process explains this behaviour. If solar pressure can't account for the tail's direction, if gravity and particle size can't justify the coherence, and if the tail is actively pulsing, then something else is shaping it. One radical proposal came from a European research group in early November. 3I-ATLAS might be emitting material bidirectionally, with jets firing both sunward and anti-sunward in a controlled feedback loop. This would allow for tail structures that respond not to solar wind, but to internal navigation systems. In other words, the tail isn't passive, it's engineered. That theory gained traction when ultraviolet imaging from the ESA's solar orbiter revealed faint electromagnetic sheaths along the tail edges, like rail lines guiding a current. These sheaths were symmetrical, precise, and stable across several observation passes. If correct, it would mean the tail isn't the result of erosion, but of design. A system of emission that uses sunlight not as a source of destruction, but as a reference point for vector control. This flips comet physics on its head. In every prior case, the tail told us about the comet's weakness, its surrender to the Sun. But 3I-ATLAS might be different. Its tail isn't bending because it's being pushed, it's bending because it chooses to. And that choice may be revealing the presence of something we've never seen before, a spacecraft disguised as a comet, or something even stranger. In space, light doesn't just illuminate, it informs. When light from the Sun interacts with matter, part of it is absorbed. Each element and molecule captures specific wavelengths, leaving behind telltale fingerprints known as absorption lines. By examining these patterns, astronomers can decode the composition of objects they've never touched. And when scientists pointed their spectrometers at 3I-ATLAS, they didn't get what they expected. The Very Large Telescope in Chile, working in tandem with the Hubble Space Telescope, performed high-resolution spectroscopic measurements of the object throughout late October and early November. The goal was simple: determine what gases and ices were present in the coma, and whether their ratios matched known cometary profiles. But the spectrum was off. Certain lines, especially those corresponding to carbon monoxide, methanol and formaldehyde, were either missing or suppressed. Others, like ionized carbon dioxide and sodium, appeared enhanced far beyond typical levels. In fact, the sodium absorption was so strong it overwhelmed neighbouring lines, creating a flat-bottom dip in the data, something typically only seen in metal-rich asteroid collisions, not frozen comets. The object was absorbing sunlight, yes, but it was doing so selectively. And that's the mystery. Comets don't have preferences. Their absorption spectrum is defined by their ingredients, but 3I-ATLAS seemed to edit the light, blocking some wavelengths, letting others pass. A process that suggested not just passive absorption, but modulation. To verify the anomaly, researchers compared the spectra across multiple instruments: Keck Observatory, JWST, and the Infrared Telescope Facility in Hawaii. All confirmed the same result. The absorption was structured. Instead of the usual scattered line profile, a mess of overlapping dips and thermal noise, the spectrum of 3I-ATLAS was segmented, like layers of filtering had been applied. This segmentation matched no known outgassing behaviour. Instead, it resembled the energy profile of a selective absorption material, something that absorbs one range of light while reflecting or transmitting the rest. That's a hallmark of engineered surfaces. Solar panels, for instance, are designed to absorb specific wavelengths that correspond to peak energy conversion. Heat shields on satellites are tuned to reflect infrared while soaking visible light. The idea that 3I-ATLAS's surface, or coma, is tuned is not far-fetched. What's far-fetched is that a natural object could achieve that on its own. One theory suggested that fine dust within the coma contains nanostructured silicates, possibly created during interstellar travel. These could, in theory, alter the object's spectral profile. But even advanced silicates wouldn't explain the temporal consistency of the absorption pattern across different angles, distances, and days. It didn't change. This is not what we expect from a dust-dominated coma. Normally, coma composition fluctuates with solar heating, but 3I-ATLAS held its profile, as if its energy processing wasn't chemical, but deliberate. And here's the strange twist. There was no thermal signature consistent with this level of energy absorption. In other words, it was absorbing light without heating up. That's nearly impossible. When objects absorb radiation, they re-emit it as heat. But 3I-ATLAS's infrared glow remained stable, cooler than it should be. This led to a chilling possibility. The energy wasn't being converted into heat, it was being used. As if some portion of the absorbed solar radiation was being stored, redirected, or transformed into a form of internal work. This isn't proof of technology, but it is proof of inconsistency between what should happen and what did. And in astrophysics, that's where discovery begins. Because the energy spectrum doesn't lie. It shows us what an object is doing, not just what it's made of. And what 3I-ATLAS is doing doesn't make sense unless it's designed to. Objects that move through space are bound by momentum, and momentum does not ask permission. Every celestial body is shaped by the combined forces of gravity, mass, and inertia. These forces interact continuously, forming orbits, deflections, and hyperbolic exits. But in all cases, the outcome is clear. An object's path follows its energy profile, unless it doesn't, and 3I-ATLAS once again doesn't. On November 14th, data from the Deep Space Network's Goldstone complex showed that 3I-ATLAS was not merely coasting through its trajectory, it was maintaining a precise inertial lock, a balance between velocity and solar gravity that looked too stable to be accidental. To be clear, 3I-ATLAS is not in orbit. Its hyperbolic trajectory proves that it is on an escape path, an interstellar visitor with no return. But within that escape arc, scientists observed something deeply unusual. The object was not accelerating in response to gravitational gradients as expected. Instead, its momentum profile appeared fixed, locked in a narrow corridor of motion that defied typical tidal influences. Here's why that matters. Comets on escape trajectories still show minute course deviations. As they pass near planets or interact with solar wind streams, even minor perturbations, dust shedding, asymmetric jets, micrometeoroid hits, can cause cumulative arc shifts. These are measured in arc seconds per day, but over weeks they distort the escape path. Yet 3I-ATLAS has remained in its calculated corridor since September 28th, despite multiple solar events, including the triple CME wave of early November. Its path has not deviated by more than 0.03 arc seconds, a figure too small to be random and too consistent to be explained by natural inertia alone. Enter the theory, gravitational inertia lock. This concept is not part of standard celestial mechanics. It's a term now being used informally by researchers to describe what appears to be active stabilization within a gravitational field, not by thrust or drag, but by adjusting internal mass distribution or inertia frames to maintain trajectory fidelity. Some spacecraft can do this, using spinning flywheels, moving ballast, or even liquid redistribution to adjust their inertia tensor, but comets cannot, unless they are something else. And this brings us to the object's mass problem. Spectral absorption suggests a low albedo surface, meaning it's not very reflective. That would normally imply a dense, rock-rich core, but its escape velocity suggests otherwise. By all accounts, the object behaves like a mass-controlled body, one that alters its mass distribution to maintain balance, even under solar force fluctuations. On November 12th, ESA's Gaia satellite, which typically tracks stars, logged a gravity lensing event, an ultra-precise measurement of 3I-ATLAS's gravitational profile as it occluded a distant star. The resulting curvature was shallower than expected, implying a hollow interior or non-homogeneous mass field. This matters because mass dictates motion, and if the mass isn't behaving like it should, if it's shifting, shielding or segmenting, then its motion will show it, which it has. Because not only is 3I-ATLAS maintaining linear momentum, it's resisting rotational drift. Multiple observatories, including the Lowell Observatory and JPL's trajectory monitoring team, have confirmed that the object's spin state remains effectively null, even after known force encounters. No object does that naturally, unless it's compensating. The gravitational inertia lock is not just a theory, it's a placeholder for something we don't yet understand, a placeholder for precision in a system that should be random, a frame of reference that seems chosen. The math holds, the motion persists, and the implications may reach beyond what physics currently explains. Because if a body can lock its motion in gravitational space, if it can use inertia as a tool rather than a consequence, then we're no longer talking about celestial drift. We're talking about navigation. When science fails to describe a shape, it usually means one of two things. Either the data is flawed, or the object isn't supposed to be there. In the case of 3I-ATLAS, shape analysis should have been straightforward. Dozens of telescopes, from ground-based observatories in Chile and Hawaii to orbiting platforms like the James Webb Space Telescope and ESA's Solar Orbiter, have been observing the object across multiple wavelengths. With the sheer volume of data, a 3D shape model should have emerged by early November, but it hasn't. Instead, every attempt at shape reconstruction has collapsed into contradiction. Here's why that's not normal. Cometary shape models are usually derived from light curves, variations in brightness as the object rotates. These can be mapped against the object's trajectory, surface activity, and coma dynamics to generate a probable 3D form. For 3I-ATLAS, this approach failed immediately. The light curve was flat. As mentioned in previous chapters, this implied either a spherical shape or a fixed solar-facing orientation. But Hubble's imaging ruled out both. The nucleus was clearly irregular. Shadows moved across the surface. Light gradients suggested texture and asymmetry, but still, no rotation signature, which means the shape wasn't varying in a way that matched its geometry. Next came the Doppler radar modelling, initiated by the Goldstone Deep Space Communications Complex during the early days of November. Normally, radar echoes return detailed profiles of cometary surfaces, showing ridges, craters, and roughness. But in the case of 3I-ATLAS, the radar return was anomalously smooth. Too smooth. The signal strength suggested a large diffuse body, but the echo shape was featureless, flat, not noisy, not chaotic, just geometrically sterile, as though the surface was either perfectly uniform or somehow absorbing the signal without meaningful reflection. This caused suspicion of a cloaking effect, either due to a plasma field, a microparticle suspension, or some unknown material capable of scattering radar differently from rock or ice. But even those theories couldn't account for the consistent failure of optical 3D models, because when combined, infrared, radar and visible light data, shape models usually converge. Here they diverged. One model from the University of Bern suggested a squat triangular prism. Another from Caltech proposed a flattened torus. A third, using JWST diffraction data, hinted at a multi-lobed cluster, not unlike Comet 67P, but none of them fit the observed coma shadowing, nor the light emission angles. And then came the final contradiction. In a multi-frame analysis by the lunar-based optical array, researchers noticed a phase-locked reflectivity pattern. In plain terms, that means the object reflected light as though its entire surface was working in sync, adjusting brightness with solar position rather than surface texture. In other words, the object's shape couldn't explain the light. It was too reactive. That's when the phrase shape suppression artifact began appearing in private research logs, a placeholder term to describe an object whose surface behaviour nullifies geometry-based inference. A term that, by definition, implies deliberate interference with how shape is perceived. Because in physics, shape leaves fingerprints. It affects mass, reflection, rotation, heat dissipation. You can't hide a shape unless you're trying to. And yet, 3I-ATLAS appears to be doing just that. Every image, every model, every radar pulse returns a different truth. Not because our tools are broken, but because the object is resisting coherence. And if an interstellar body is deliberately resisting shape classification, then it may not be a comet at all. It may be something that wants to look like anything but what it is. Dust is the signature of a comet in distress. As solar radiation strikes a nucleus, volatile ices vaporize and lift fine particles into space. These particles scatter light, forming the visible coma and tail, tracing the object's activity and size. From this process, astronomers derive a critical ratio, the dust-to-nucleus mass. And in nearly every comet observed, that ratio falls within predictable bounds. Except this one. The 3I-ATLAS dust profile doesn't make sense. Observations from the Gran Telescopio Canarias, along with supporting photometry from amateur stations across 3 hemispheres, revealed an unusually dense coma surrounding the object as early as late October. Based on light scattering models and dust reflectivity, the estimated total dust mass exceeded 200 million kilograms. That would be unremarkable if the nucleus were large. But that's where the numbers break. High-resolution imaging from the Hubble Space Telescope and JWST placed the nucleus diameter at no more than 1.6 kilometers, on the smaller end of interstellar objects. A nucleus of that size, even with high outgassing rates, simply shouldn't be able to lift that much material in such a short time. The dust-to-nucleus ratio, when modelled, returned a value of over 15:1. By contrast, Comet 67P, famously photographed by ESA's Rosetta mission, maintained a ratio closer to 1:3 during its active phase. Halley's Comet sits around 1:6. No known comet or interstellar visitor has ever recorded a value close to what 3I-ATLAS is producing. So where is the dust coming from? Several hypotheses were proposed. First, perhaps the object is undergoing fragmentation, breaking apart internally and releasing debris, but there's no visual or spectral evidence of fracturing. No sudden brightening, no outburst, just a steady, controlled envelope of particles. Second, perhaps the coma is made of unusually fine particles, nanometer-scale grains that reflect more light per unit mass. This would skew brightness models and inflate the apparent mass. But once again, the infrared signature disagrees. Fine particles re-radiate absorbed sunlight quickly, producing higher mid-infrared flux. Yet JWST's thermal imaging showed a cold coma, far too cold for a cloud of ultra-fine sunlit grains. Then a third possibility emerged. What if the dust is not being emitted from within, but rather being drawn in from external sources? This raised eyebrows. Comets don't gather material, they expel it. But several observatories, including the Atacama Pathfinder experiment, noted something subtle: radial infall. Some of the particles surrounding 3I-ATLAS were not expanding. They were moving inward, as if orbiting or spiralling toward the nucleus. That isn't normal. Dust doesn't fall back into comets. There's no gravity well strong enough to sustain it. And yet, in this case, the coma showed both outward drift and inward retention, a behaviour more akin to an atmosphere than an ejector field. If accurate, it implies an unknown mechanism is at work, possibly electromagnetic capture or static field entrapment. That would mean the object is not just releasing material, it's managing it, keeping it suspended, balanced, not by accident, by intention. And that brings us to the final problem. If the dust mass doesn't match the nucleus, and the spectral profile contradicts all known ejection models, then the source of the material must be non-physical. Either the nucleus is larger than we can see, hidden under an optical illusion, or it is not a nucleus at all, but a central structure, coated or shrouded in a shell of material for reasons we do not yet understand. Perhaps as camouflage, perhaps as a shield, or perhaps as a kind of solar sail, forming and reforming to adjust the object's motion. Whatever the truth, one fact is clear. The dust mass doesn't match, and in space, when the math doesn't balance, it's usually because the equation is missing something we haven't yet discovered. Everything that moves through a fluid leaves a wake. In space, the fluid isn't air or water, it's plasma, dust, and photons. And when a solid object moves through that medium, subtle disturbances form in its trail. These are not random. They're shaped by motion, mass, temperature, and composition. By studying them, scientists can often determine what an object is made of, even how it moves. But 3I-ATLAS has left behind a wake that doesn't behave like anything we've seen before. The first clue came from SOHO's LASCO C3 coronagraph, which captured the object as it passed near the Sun's magnetic equator. Behind it, instead of the expected dispersing trail of dust and ionized gas, the telescope registered fine filamentary structures, long, coherent streamers of material that remained intact far beyond the zone of expected solar disruption. These filaments didn't fade with distance, they pulsed. At exactly 10-minute intervals, instruments on board ESA's solar orbiter detected a series of low-density plasma fluctuations trailing behind 3I-ATLAS. Each fluctuation corresponded with a faint drop in local solar wind pressure, as if something was temporarily resisting the flow, then releasing it. That behaviour is not consistent with natural dust shedding. In normal comets, the wake expands, diffuses, and eventually dissolves into the heliospheric flow. The particles behind a comet behave like sand thrown into a river. They spread out and vanish. But this wake wasn't fading. It was reforming, almost like it had internal structure. And then came the second anomaly. When the infrared telescope facility in Hawaii took long-exposure imaging of the area behind 3I-ATLAS, the residual heat signature did not show a uniform tail. Instead, it showed nodal clustering, a repeating pattern of high and low temperature regions spaced evenly every 400 kilometers. This kind of periodicity is not known to occur in passive dust trails. The only comparable analogue comes from low Earth orbit, where wake turbulence behind satellites can create similar patterns, caused by ion thrust, radiative shielding, or electromagnetic interference. This raised the possibility that 3I-ATLAS isn't simply moving through space, it's interacting with it. Because these wake patterns imply drag management, the kind of pattern you'd expect if the object were regulating how much pressure it displaces behind it. If the object is adjusting its boundary layer, either magnetically or electrostatically, it could in theory channel solar particles in specific patterns. One experimental probe, NASA's Parker Solar Probe, even detected a reverse plasma wave emanating from behind the object on November 9th. This wave, which appeared to push against the solar wind for several seconds, originated not from the nucleus, but from behind it, as if the wake wasn't following the object, but communicating with it. And this challenges a core assumption in celestial dynamics, that wakes are passive. Because in 3I-ATLAS, the wake behaves like a reaction field, a responsive, coherent trail that fluctuates in sync with the object's orientation. This could only happen if there's some kind of feedback loop between the comet and its environment, and that opens two possibilities. Either we're seeing a natural field interaction on a scale we've never recorded, or the object is generating the pattern intentionally, to reduce drag, maintain trajectory, or perhaps even mask its real signature. Because if you can control your wake, you can control what follows you, and that may be the most unsettling idea of all. A wake is supposed to be evidence of where you've been, but for 3I-ATLAS, it might be a message about where it's going. Space agencies release orbital parameters all the time. They're routine, simple sets of numbers describing where an object is, where it's going, and how fast. These are published to databases so observatories of spacecraft and amateur trackers can coordinate observations. Transparency is key. Consistency is expected. Which is why what the European Space Agency did on November 12th stands out, because they changed the numbers, silently, without a press release, without explanation, without telling anyone why. It began with a routine check of ESA's Near-Earth Object Dynamics system. An Italian researcher noticed that the orbital eccentricity of 3I-ATLAS, the degree to which its path deviates from a perfect circle, had been updated. Originally listed as 1.01, a value consistent with a slightly hyperbolic trajectory, it was suddenly adjusted to 1.23. That might seem like a small correction, but it's not. It means that the object isn't just leaving the solar system, it's doing so with far more energy than originally estimated. Put differently, 3I-ATLAS isn't just on a flyby path, it's on a departure vector that suggests it may have never been gravitationally captured at all. Why would ESA update this value? One possibility is simple error correction. As more observational data comes in, orbits are refined. But here's the problem. The change was not accompanied by a revision history, which is standard practice. The previous entry was overwritten, erased. The only way the change was detected was because several independent researchers had scraped and stored the earlier dataset. And it wasn't just the eccentricity. The argument of perihelion, which describes the orientation of the closest approach to the Sun, was also updated. It shifted by 3.7 degrees, a value far outside the margin of error for any natural perturbation. What caused that? ESA didn't say. When contacted, representatives from the NERC Space Geodesy facility responded only with a link to the current data page. No statement, no public comment, no explanation. Then the real revelation came. When analysts compared the new trajectory model to the previous one, something strange emerged. The object's closest approach to the Sun, previously modelled to occur on November 6th at 1422 UTC, was now listed as having occurred on November 4th at 1109 UTC. That's a 49-hour discrepancy, retroactively applied. It's not a refinement, it's a timeline shift. That's when suspicions began to grow. Had ESA seen something during perihelion that changed their entire model? And if so, why not say so? One answer may lie in the data blackout that occurred during that window. On both November 4th and 5th, several ground-based solar monitoring stations in Spain, France and Poland reported sudden service interruptions, citing unexplained bandwidth loss and packet drift. These stations typically relay solar weather data, including tracking of inbound and outbound objects. This isn't conclusive, but it does raise a pattern. The parameter change happened after those outages. So what exactly did ESA see? And why quietly rewrite the rules? A final note comes from an internal document leaked to a private astronomy network, an observation summary referencing a classified perturbation index related to 3I-ATLAS's solar passage. The term perturbation index is not standard ESA language. It implies anomalous orbital behaviour, possibly gravitational or electromagnetic, that defied existing prediction models. But nothing about that appears in the public logs. What does appear is this: a new orbital model, a new energy signature, a new direction, and no explanation. In astronomy, changes like this don't happen quietly, unless someone wants them to. And in the case of 3I-ATLAS, ESA's silence may be the most revealing data point of all, because when an object begins to defy physics, sometimes the only way to stay ahead of the questions is to stop answering them altogether. On the morning of November 10th, at exactly 0312 UTC, a signal came back. It wasn't from Earth, it wasn't from deep space. It came from the objects known as 3I-ATLAS, and it wasn't a transmission. It was an echo, a microwave bounce recorded by the Goldstone Solar System radar, which had sent a high-frequency pulse toward the object's projected location. Microwave radar is used to map asteroids, comets, and even planetary surfaces. It works by firing directed energy toward a target and analysing the returned signal. Most of the time, the signal is scattered, randomised by surface roughness, absorbed by dust, or lost to the vacuum. But not this time. The signal came back clean, too clean. And that's what set off the alarms. The returning microwave echo showed a specular reflection, a mirror-like bounce, as if the surface of 3I-ATLAS were flat, solid, and aligned. Such reflections only occur when a surface is both smooth at the wavelength scale and precisely oriented, which no known comet ever is. Initial analysis by the Jet Propulsion Laboratory revealed that the reflection was strongest at 9.4 GHz, with harmonics trailing off at predictable intervals, exactly as if bouncing off a structured surface. There was no scattering, no diffusion. The waveform matched only one known signature, a polished metal composite. This defied explanation. Cometary surfaces are uneven, porous, layered with dust and ice. They scatter microwaves unpredictably. Even asteroid Bennu, one of the smoothest natural bodies we've studied, produces noisy returns, but 3I-ATLAS responded like a disk, angled perfectly to bounce the signal back in phase. That same day, a second facility, Tianwen-1's radar module, operating from Mars orbit, attempted a passive recording. It captured a secondary echo several milliseconds later, arriving from a slightly displaced angle. This second pulse, while weaker, was offset in frequency by 2 kHz, a shift that suggests internal resonance. In simpler terms, the object rang, like a bell. When struck by microwave energy, it didn't just reflect, it vibrated, producing a trailing oscillation not accounted for by natural structure, a response that echoed inwards before decaying. Some scientists began to whisper the word cavity. Others used the phrase hollow core resonance. But one theory stood out: a microwave waveguide, a type of internal tunnel or chamber specifically shaped to capture and reflect radio waves. These exist in human engineering. Satellites use them, space telescopes use them, but a comet. It would mean that 3I-ATLAS isn't just a body, it's a chamber with internal geometry. And then came the silence. Within 12 hours, the microwave logs were retracted from Goldstone's public servers. JPL's press team issued no statement. The frequency band was reclassified under non-diagnostic response, a bureaucratic label typically used when results are deemed inconsistent with mission goals. But the data had already circulated. Independent analysts replicated the signal curve. Amateur radio astronomers with access to archived SDR logs found matching reflections, some as far back as October 18th, buried in noise. The pattern was there, it had always been there, we just hadn't looked closely enough. The implications are staggering. If the echo was real, and all data says it was, then we're not dealing with a porous, chaotic mass of rock and ice. We are dealing with a structure, one that responds to energy with precision, not randomness. And structures don't form by accident, they are built. So now the question shifts from what is it made of to why is it reflecting microwave energy as if it's waiting for it? And perhaps more unsettling, who is it reflecting it for? Most comets don't survive their closest approach to the Sun. The combination of solar heat, tidal forces and internal pressure is too much. We've seen it time and time again. The moment of perihelion, when a comet passes nearest to the Sun, becomes the moment of destruction. The nucleus fractures, splinters, fades. Pieces break off and spiral into separate paths, forming the telltale cloud of fragmentation debris. But that didn't happen with 3I-ATLAS. It should have. By early November, nearly every major observatory tracking the object was preparing for a fragmentation event. The models were clear. Based on mass estimates, angular velocity and proximity to solar gravity, the object's structural stress should have peaked around November 4th. Yet instead of breaking apart, 3I-ATLAS emerged from perihelion intact. Worse, there was no visible damage, no cracks, no off-axis spin, no outburst signatures, nothing. And this failure to fragment may be the most revealing anomaly yet. To understand why, we need to examine the physics of cometary cohesion. When comets heat up, internal volatiles sublimate, turning from solid to gas. This builds pressure under the crust. If the structure is brittle, it cracks. If the nucleus is already fractured, it separates. That process is random, violent, and thermally driven. For 3I-ATLAS, infrared and UV data from SOHO, Stereo-A, and the Solar Orbiter all recorded substantial surface heating. Surface temperatures exceeded 300 Kelvin in late October. Gas outflow increased. Spectral analysis showed the presence of volatiles like carbon monoxide and methane, classic pre-fragmentation markers. But fragmentation never came. Instead, the emission curve flattened. By November 5th, gas outflow levels had dropped, not spiked. The coma thinned. The light curve stabilized. Not only had the object survived its solar passage, it had calmed, and that's not natural. Many astronomers initially assumed they had missed the breakup, that it had occurred while the object was behind the Sun. But when it re-emerged, the images told a different story. There were no fragments, no trailing debris, no orbital scatter, just one object, still whole, still smooth, still aligned. This contradicted every prediction made by models from the Harvard-Smithsonian Center for Astrophysics, the Max Planck Institute, and ESA's Planetary Defense Office. All had forecast some level of breakup. The math said it had to happen, so why didn't it? One theory emerged: reinforced internal structure. That is, 3I-ATLAS may not be held together by gravity or ice cohesion, but by something far stronger. A lattice, a frame, a skeleton not made of rock, but of something unknown. A kind of internal scaffolding that resists pressure from within and thermal expansion from without. Another possibility is thermal damping, the controlled dispersal of heat across the body. In natural objects, heat builds in hotspots. In engineered systems, heat can be redirected. If 3I-ATLAS was distributing solar heat uniformly, it could have reduced internal stress and avoided fracturing altogether. But that assumes intentional design. And that brings us to the most troubling implication. The object didn't survive fragmentation by chance. It avoided it. It passed through the most destructive corridor in the inner solar system, where countless comets before it have failed, and emerged perfectly stable. That is not the behaviour of a rock. That is the behaviour of something that understands its environment, and something that understands how to survive it. So when scientists ask where is the debris field, they're asking the wrong question. Because if 3I-ATLAS didn't fragment, it means it was never going to. And maybe it was never meant to. The sun pushes everything away. Its solar wind, composed of high-speed protons and electrons, radiates outward through the heliosphere, sweeping dust, gas and particles along with it. Comets, asteroids and spacecraft are all affected by this relentless pressure. It's why comet tails always point away from the sun. But on November 8th, something happened that shouldn't be possible. The solar wind struck 3I-ATLAS and bounced. Data from NASA's Parker Solar Probe, which was monitoring solar plasma density near the inner heliosphere, recorded an anomaly at 742 UTC. A brief reversal in local proton velocity, lasting approximately 49 seconds, registered just downstream from the object's path. In simple terms, the solar wind hit something and came back. At first, researchers believed it was an instrumentation glitch, but the anomaly was cross-confirmed by Stereo A and ESA's solar orbiter, both of which recorded a drop in plasma continuity behind the object at nearly the same time. The density profile dipped, then surged, then dipped again. This pattern, known as a shockfront signature, usually forms behind blunt objects moving at hypersonic speeds through gas. But in this case, the shockfront was upstream. This implies something extraordinary. 3I-ATLAS wasn't being pushed by the sun, it was pushing back. How? One possibility is the presence of a magnetosphere, a bubble of magnetic field that can deflect solar wind, much like Earth's magnetic field protects us from solar radiation. But comets don't have magnetospheres. They're not large enough, they don't rotate fast enough, and they don't generate internal magnetic fields, unless 3I-ATLAS isn't a comet at all. Analysis of the deflected particle paths showed an angle of reflection consistent with coherent magnetic field redirection. It behaved like a magnetic mirror, a field boundary where charged particles are reflected without physical contact. And here's where it becomes more troubling. The magnetic signature wasn't static, it was modulated. Parker recorded rhythmic pulses of field strength, spaced precisely 22 seconds apart, over a 90-second interval. These are not natural harmonics. They don't arise from rotation. They arise from modulation, like a radio transmitter changing frequency. In other words, it wasn't just repelling solar wind, it was controlling the interaction. Then came the secondary signature. An unexpected thermal rise recorded behind the object showed a plasma bloom expanding laterally at over 40 kilometers per second. This bloom formed a symmetric arc, similar to the wake left behind by an aircraft using thrust vectoring. If 3I-ATLAS had ejected material to maintain trajectory, that would explain the bloom. But no material was detected, no debris, no gas, just force, applied without exhaust. This points to a possibility many scientists hesitate to voice. The object may be using a form of field propulsion, not unlike the theoretical MHD, magnetohydrodynamic drives proposed for spacecraft. If true, 3I-ATLAS isn't just moving through space, it's moving with intent. And the sun, our greatest source of cosmic pressure, is being treated not as an obstacle but as a reference point, a system to push against, a source of leverage. All this brings us to the simplest but most profound conclusion. The solar wind isn't always in control. Sometimes something pushes back, and when that happens, we're forced to reconsider everything we thought we knew about natural motion in the solar system. Because 3I-ATLAS just taught us that the void is not empty, it's a medium, and someone, or something, knows how to navigate it better than we do. It wasn't spinning, it wasn't emitting jets. But 3I-ATLAS was pulsing. Astronomers first noticed it on November 6th, while analysing stacked imaging data from the James Webb Space Telescope. They weren't looking for motion, they were analysing spectral variation in the coma. But every 10 minutes, a subtle shift occurred. The surrounding dust would expand slightly, then contract as if exhaled. And that's when someone called it the breath effect. At first it seemed impossible. No known natural body in space exhibits rhythmic, self-consistent expansion patterns without internal pressure systems or mechanical rotation. Comet outgassing is chaotic, driven by sunlight, temperature and surface composition. There is no timer, but 3I-ATLAS had one. In image after image, the pattern repeated. A faint glow would rise around the object, then recede, like a breath. One cycle every 9 minutes and 53 seconds, pulsing, alive. This prompted infrared analysis from the Infrared Telescope Facility, IRTF, in Hawaii. Their spectrograph confirmed temperature fluctuations. Small, just a few Kelvin, but consistent with the optical pulses. These weren't caused by solar flares, instrument drift, or viewing angle. They were intrinsic to the object. That changed everything. Thermal. Models proposed two hypotheses. 1. 3I-ATLAS was undergoing periodic sublimation, layers of volatile material heating and cooling in sync, releasing gas in a timed rhythm. But that process doesn't create uniformity, and the gases released didn't match typical volatile signatures. There was no spike in carbon monoxide or methane, no water ice, only a faint trace of ionized neon, a substance rare in comets and virtually unheard of in rhythmic cycles. The second hypothesis was more exotic, a field-based pulse, an electromagnetic interaction occurring at regular intervals, modulating the coma from within. This would require an internal power source, something capable of timing, measuring, and releasing controlled bursts. But that's not a comet, that's a device. Then came the JWST phase map. Infrared phase differential mapping taken over a 2-hour period showed that the glow wasn't spreading outward like gas. It was pushing against space itself, subtly altering the phase angle of the light behind it. This isn't breath, it's distortion, controlled distortion. As if the object were regulating its surroundings, not to move, but to communicate. Like a sonar ping. Each pulse could be a scan, a readout, or something more unsettling, a message. What confirmed this possibility was the silent zone. Radio telescopes at the Atacama Large Millimeter Array, ALMA, reported periodic drops in background cosmic noise synchronized with the pulses. Every time 3I-ATLAS pulsed, a tiny zone of radio silence formed around it, a cone of suppressed interference that lasted 19 seconds. That's not a cometary process, that's active cancellation. Whether intentional or not, the effect was real. 3I-ATLAS was not just pulsing, it was creating pockets of environmental silence, breathing not oxygen, but information, in, out, like a probe scanning its environment, like a machine preparing for something. And yet the object remained visually calm. No visible jets, no tumbling, just a slow drift, cloaked in stillness, while the surrounding field fluctuated with eerie regularity. The question is no longer whether this is natural or artificial. The question is whether this breathing pattern is for us, or for itself. Because in space, breath is life. And when an object starts to breathe, it means something inside it is still awake. Every comet leaves something behind. As it moves through the solar system, ice sublimates, rock disintegrates, and microscopic particles scatter into space. These particles stretch into a thin ribbon, a dust trail, that marks the comet's path for months, sometimes even years. This trail can be detected long after the comet itself is gone. But 3I-ATLAS left nothing. No streak, no scatter, no signature, just silence. The first indication came from the Canada-France-Hawaii telescope, which attempted post-perihelion imaging of the object's trajectory corridor on November 9th. They expected a debris, trail, an elongated field of dust lingering in the wake of the object's passage. Instead, their long exposure composites showed only empty starfield. No residual dust, no reflective grains, no plasma haze. Then came Pan-STARRS scanning from Haleakala. Same result, nothing. And this was not a matter of sensitivity. These instruments can detect faint dust trails from comets that passed through this region years ago. Yet 3I-ATLAS, which had just passed days earlier, showed no detectable remnants, no trail. This was immediately flagged as an anomaly. Even comets with low activity leave some dust. Even dry interstellar objects like Oumuamua generated a barely visible dust field through mechanical abrasion. But 3I-ATLAS appeared to have passed clean, as if it had never interacted with the Sun at all. Infrared sweeps by NASA's Neowise telescope confirmed it. The thermal band that should have lit up with residual particles in the object's orbital path returned a flat signal, ambient only. Nothing had been deposited, nothing was drifting. This prompted a radical theory. That 3I-ATLAS is not shedding mass at all. That it is closed system, meaning any material it ejects is either recovered, reabsorbed, or never leaves in the first place. This isn't a comet, it's a sealed body, and that changes everything. In comets, the dust trail is a consequence of fragility. Surface layers flake off under solar pressure. Tiny particles are carried by outgassed jets. The dust trail is not a feature, it's a symptom of degradation. But 3I-ATLAS shows no such symptom. Its outer layer seems intact. Its mass hasn't shifted. Its tail, if it can be called that, is made almost entirely of ionized plasma, not particulate matter. It interacts with light, but it leaves no residue, no grain, no dust, and that implies design. Because avoiding a dust trail is difficult. It requires structural stability under thermal stress, precise control of material release, and an ability to regulate external interaction. No random ice ball tumbling through space can manage that. This is where the analysis deepens. The EC Optical Ground Station attempted laser ranging along the predicted orbital plane on November 10th, using photon scattering to detect microscopic remnants. Not only did they fail to detect dust, they found a region of optical damping, a zone where light scatter was suppressed, as if the space through which 3I-ATLAS had passed had been cleared, cleaned, like a corridor. If true, this means the object is not just avoiding a dust trail, it may be erasing one. Either through magnetic containment, gravitational vectoring, or some unknown mechanism of boundary management, the effect is the same. 3I-ATLAS moves through the solar system without leaving a trace. And in astrophysics that's not normal, that's intentional. Which brings us to the unsettling question. If it's hiding its trail, what is it hiding from? Or more directly, who is supposed to believe it was never there? By November 12th, 3I-ATLAS was supposed to be just another fading object on its way out of the solar system. It had passed perihelion. The peak moment of drama was over. Instruments had logged their data. Spectrographs had cooled. The world was turning back toward more urgent news. But one thing didn't happen. There was no goodbye, no official report, no closure, no summary bulletin from NASA, ESA, or any major observatory, no final orbit estimate, no coordinated sign-off that would normally mark the end of such a high-profile observational campaign. Instead, 3I-ATLAS just slipped away, and the silence was deafening. The last confirmed optical image came from the Subaru telescope in Hawaii on the night of November 11th. The object was faint, low on the horizon, and already moving beyond the plane of Earth-based visibility. Observatories in the southern hemisphere attempted to reacquire it on the 12th and 13th. They failed. But not because of clouds, because the object had vanished. The projected trajectory placed it well within view. Its expected magnitude was within reach of at least 5 ground-based arrays, and yet no signal, no reflection, no return ping from radar. It had disappeared from every band. Ultraviolet, infrared, microwave, even X-ray mapping, which had once picked up faint emissions near perihelion, came up empty. It was gone. What remained was a residual plasma trail, thin, short, and decaying. But even that vanished by November 15th. The space where 3I-ATLAS had been was now indistinguishable from background. No echoes, no dust, no wake, just absence. The object's silence wasn't limited to the optical. Radio tracking from the Deep Space Network, normally able to track objects far beyond Pluto, received no return, no passive emissions, no Doppler ping, as if the object had ceased to exist. And maybe that's the point. Because this wasn't a passive fade-out, it was a deliberate exit. Some now believe that 3I-ATLAS performed a vector shift, an untracked course change executed just as it passed the final planetary plane. A manoeuvre not visible to the human eye, but traceable through gravitational echo, and those echoes were real. By November the 16th, multiple independent researchers reported anomalous data in the Lagrange point 2 corridor. Small perturbations, a missing mass effect, as if something had altered the gravitational baseline of nearby probe readings. It wasn't proof, but it was something. And then came the archival wipe. 3 observatories, one in Chile, one in Spain, and one in New Zealand, reported sudden revision of their November logs. Entries containing tracking data for 3I-ATLAS were flagged for recalibration and replaced with blank placeholders, the same placeholder, across 3 facilities. That doesn't happen by accident. The coordinated removal of raw tracking data isn't routine, it's policy, and policy only changes when something is being protected or hidden. So what was 3I-ATLAS? A comet? An interstellar probe? A piece of discarded technology from an intelligence we don't understand? We don't know, and as of November 17th, we no longer have a way to find out. Because whatever it was, it left without a sound. No energy spike, no parting burst, just silence. And in the world of astronomy, silence speaks volumes. Sometimes the loudest event in the sky is the one that ends without a single trace, because real mysteries don't explode, they vanish.